Welcome to Game Theory Simultaneous Games. This is part one. There'll be a second part on the topic of simultaneous games. In this lesson, I'm going to talk about some solutions. I have the names of those solutions down here. Dominant strategy, equilibrium, strictly dominant pure strategies, and iterated elimination of strictly dominated strategies. A strategy profile is a dominant strategy equilibrium if and only if for each player I, S sub I, is a weakly dominant strategy. So each one of these has to be weakly dominant for the associated player. And I have several examples. On the left, S13, S23 is a dominant strategy equilibrium. We can check that. S13, we look at that. 1 is greater than 0, 0. 4 is greater than 0, and 1. And 4 is greater than 1, equal to 4. But that's okay because we have only the requirement for weakly dominant. Remember, that was greater than or equal to. Then for player 2, we need to check S23. We look at the second component. It's actually strongly dominant in that for player 2, but that's okay since strongly dominant implies weakly dominant. We can see here 5 is greater than 3, is greater than 0. 5 is greater than 4, is greater than 1. And 7 is greater than 1, greater than minus 3. Then for the rock, scissors, paper, if you recall from the previous lesson, we found that there was really no dominant or even weakly dominant strategy for any of the players. And it probably made the most sense for each player to play each of the three strategies 1/3 of the time. And we didn't prove that, and in fact we won't prove it in this lesson, but we'll get to it in a following lesson. And then we have the third example here, where we do have a dominant strategy equilibrium, and that's B1, B2. So I've highlighted in bold green. We can check here. So B1 is weakly dominant for, it's actually strongly dominant for player A. You can see 4 is greater than 3, 2 is greater than 1. And then B2 is strongly dominant for player B. 4 is greater than 3, 2 is greater than 1. Okay, so this is an equilibrium, and if both of these here are for each of the games. And the assumption is, not just in these examples, but in general, the players understand the nature of the game and they reason rationally to play this equilibrium. So you would expect both players to fall into this here, where player 1 plays S13 and player 2 plays S23. And the same goes for this game here. In the prisoner's dilemma, which we've repeated again down here, Mr. A always gets a higher payout by playing strategy B1. We see that 4 is greater than 3, 2 is greater than 1, regardless of whether Ms. B plays strategy S2 or B2. So B1 is a dominant pure strategy for Mr. A. Using similar logic, B2 is a dominant pure strategy for Ms. B, which we've seen this already, but I wanted to introduce another concept here. Since the two parties cannot coordinate, that's the rule for this game, and it's typical for the simultaneous games, and they have no reason to trust each other. They both betray each other. The result is payoff 2-2. So the new term we have here is something called no regret. Neither player has any regret in their decision, even if they're told what the other player is going to do. So for example, if we tell A that B is going to remain silent, A is still going to play betrayal because 4 is greater than 3. If A is told in advance that B is going to betray, then again, A has no regret in playing betrayal because 2 is greater than 1. So that's what's called a no regret solution. And this is symmetric, so you have the same deal for B. And as we noted before, the dilemma is that both prisoners could do better by remaining silent, 3-3, that's better than 2-2. But since they can't cooperate and they don't trust each other, they can't take that chance. And if one remains silent, as we saw, the other one is going to betray. So that's the dilemma of this particular game. I have an exercise for you to try. Find the no regret solution for the following game. It's a two-player game. Player 1 can go choose up or down, and player 2 can choose left or right, and then these are the payoffs here. Okay, so it's pretty easy. You should be able to figure it out just by studying this a little bit, and it has a similar dilemma to the prisoner game that we just saw. In the prisoner's dilemma game from the previous slide, each player was able to decide to betray the other without even looking at the payouts of the other player. They just saw that their payout was greater in each case, so they chose a particular strategy to defect. In other games, it takes several steps to arrive at a rational, no regret solution. And I have an example of this on this page and the next. So on the left here, consider the payoff matrix. Player 1 has strategies S sub 1, 1, S sub 1, 2, S sub 1, 3, and player 2 has these strategies shown here, and these are the payoffs. And what you can see from this analysis, and keep in mind both players can see the playoff matrix, and so they can. The assumption is they arrive at similar conclusions. So if player 1 looks at this and sees that player 2 always does better with strategy S21 over strategy S22. You see 5 is greater than 1, 4 greater than 3, 1 greater than 0. So player 1 can assume player 2 is not going to play this strategy here, S22. And that brings us to this second matrix here. So we haven't found a no regret solution yet, but we've simplified the problem. We've eliminated one of the strategies for player 2 because it's dominated by S21. So let's continue with this matrix on the right on the next slide. I carried over the matrix from the previous slide. I put it here. So we can see that player 1 has a strategy S11 in this modified matrix that dominates strategy S12. You notice 8 is greater than 7, 2 is greater than 1. So both players see this and they both reason logically. They're not able to communicate, but they can reason logically. And so the assumption from, or the deduction, I should say, from player 2 is that player 1 is not going to play strategy 1, 2. And so that brings us to this matrix here. Now player 1 sees player 2's position where 7 is bigger than 5, 5 is bigger than 1. So player 1 concludes that player 2 in this reduced matrix is not going to play S23, or is going to play S23 since it dominates S21. And so this column is now eliminated. And then we're down to this here. And from here we can see that player 1 has 3 being greater than 2. So player 1 is going to want to play strategy 1, 3. And player 2, it has only one choice, right? It's the S2-3. That's all that's left. So 3-5 would be the no regrets solution in this case. But as we saw, it took several iterations to get to this point. I have an exercise for you. This is actually quite involved, but the process is straightforward. You want to eliminate the various rows and columns to eventually arrive at a no regret solution. So if you want to try this, I would suggest you pause here because I'm going to show you not the details, but I'm going to show you the sort of a sketch of the solution. Okay, I'm going to show you the hint or the sketch of the solution here. Here it is. So D eliminates C, is eliminated by C, excuse me. So let me point to that. We'll just go through one of them. So 2 is greater than 1, minus 1 is greater than minus 3, minus 3 is greater than minus 4, 4 is greater than 0, and 0 is greater than minus 3. So D is eliminated. Then you can just cross this out if they're doing this on paper. And then you would, next you can eliminate F by either G or H. And then you eliminate E by B. Again, you're crossing out rows and columns as you go along. Then you eliminate G by H, A by B, and so on. And eventually you get the solution BJ27. So that's the no regret solution. I have a couple of examples on this slide. I didn't go through all the details in either example, so you may want to do that just to reinforce your understanding. The first one is table 1, and that example shows that you don't need to have the same number of options or strategies for each player. And we can do an elimination here on this matrix. You notice B is for player A, B dominates A, so we can eliminate A. And then once we eliminate A, X dominates Y, so we can eliminate Y. And then finally we can eliminate C, and we're left with the no regret solution BX. Okay, so I kind of jumped over the details, but again, you may want to do that in detail just to test your understanding. Then the second example, these two matrices here, I want to talk about next, and that's the process we've used here and on the previous slide and on this example is called the iterated elimination of strictly dominated strategies, which I abbreviate as IESDS. And that does not necessarily lead to a no regret strategy profile, and show that here. So you notice that first B strictly dominates C. 4 is greater than 2, 5 greater than 0, 4 greater than 3. So we can eliminate C. Once C is eliminated, Y is seen to dominate Z. So you can see 4 greater than 2, 2 greater than 0. We don't need to consider this row. And then after eliminating strategies C and Z, we have this situation here, but now we're stuck because if you look at player A, B is not dominant because 4 is less than 5, but then 5 is greater than 1, so A is not dominant either. And you have the same problem with player 2. 4 is greater than 3, but 2 is less than 3, so Y doesn't dominate X and vice versa. And so we have no regret solution in this particular example. So this is a type of example where you get into using probabilities of playing each one of the strategies a particular percentage of the time. but that's something for a future lesson, which I'll get into. I just want to illustrate here that this process doesn't always give you a solution. I have another example on this slide. Different orders of eliminating dominant strategies in two-person games can lead to different reduced games. However, the order of elimination does not matter for strictly dominated strategies. And for elimination of weakly dominated strategies in zero-sum games, I'll give you a reference to a paper. I'll put it in the information to this video. So the game in Table 1 can be reduced with varying results using iterated elimination with a combination of weakly and strictly dominated strategies. So what we're going to see on this slide and the next is we can come up with different answers. And as I hinted to here, the problem is using these weakly dominated strategies. That's where you run into trouble. So in one reduction path, we first eliminate B since it's weakly dominated by A. You notice we have equality here, but then here A is greater than B, so we can eliminate B. That gets us down to this row here. Next, we eliminate X and Z since they are weakly dominated by Y. You notice, again, we have to look at the second. When you're working with columns, you have to look at the second parameter here in the tuple. So 0 is equal to the other two, and then 3 is bigger than 1, greater than 2. So Y weakly dominates X and Z, and we eliminate these two, and then we look at player one, and so player one would select strategy A, and player two has only one strategy left. So 2-0 would be the no regret solution in this case. All right, now we can do this in another order, and I'll show you that on the next slide. But just keep in mind the solution we got here. So we can go about doing this reduction in a different order, and that's what I have here. I started with the same matrix again, and we eliminate Z now, since it's weakly dominated by Y, looking at the second term in the tuple, 0 equals 0, 1 equals 1, but 3 is greater than 2. So we eliminate Z. And then we can eliminate C either by A or B. You notice 1 equals 1, but 2 is greater than 0. So C is gone. And then finally, we can eliminate Y, since 0 equals 0 and 2 is greater than 1. So Y is gone. And then we end up here. Player 2 has to play X. That's the only thing left. And then player 1 is happy with either A or B because they have an answer, or a payoff, I should say, of 1 in either case. So we kind of get two possible solutions here. If you recall from the previous slide, we didn't get either one of these. We got 2-0 is the solution. So you run into these problems when you need to use weakly dominated strategies in order to do your reduction. Okay, so that was the final slide in this lesson. I have a second lesson on simultaneous games. It gets into some additional details, including probabilities, where you play different strategies at different percentage of the time in order to optimize your result for both players.